And very gladly, the Hubble Space Telescope was looking at it because some places on Earth were cloudy, and I know from observers that couldn't really take good data of it. But just a few hours ago, I received an analysis of the first data from the Hubble Space Telescope on January 22nd, and it looks very interesting.
After the January 22 alignment, new analysis of telescope data suggests that the interstellar object 3I Atlas may be far more complex than previously reported, with high-resolution images revealing multiple overlapping jets and faint structural features that were not visible in earlier observations. Astronomers analyzing newly available telescope data have identified a previously unreported structural feature in the interstellar object 3I Atlas. It does not emit just three jets, as widely circulated images suggested, but a far more complex system of overlapping outflows. High-resolution observations taken during the late January Earth-Sun 3I Atlas alignment, combined with raw imagery from the Hubble Space Telescope, show multiple distinct jets emerging from different regions of the nucleus, with additional faint structures becoming visible when minimal processing is applied. The finding challenges the now popular interpretation of a clean three-jet symmetry and suggests that 3I Atlas is undergoing a level of directional activity rarely seen in known comets, raising new questions about its physical structure and the processes driving its behavior. Independent astronomers watching from the ground had been following 3I Atlas for months, often with modest backyard telescopes. Weather, however, rarely cooperates with celestial timing, and in many parts of the United States, the critical January 22 window was clouded out. Some of the best personal images were captured a couple of days earlier on January 20, when skies were clearer. Even those earlier images hinted that something about 3I Atlas was not entirely straightforward. The object was active, but its activity did not resemble the clean, simple cometary shapes familiar from long-period comets, or even from the second known interstellar visitor, 2I Borisov. While ground-based observers waited for clear skies, another set of eyes had already been trained on the object. The Hubble Space Telescope had observed 3I Atlas several times over the previous year, and its data were quietly accumulating in the public archive. Images taken in July 2025, when the object was still far from the Sun, used relatively short exposures and showed a compact nucleus with hints of surrounding material. Later observations on November 30 and December 4 used much longer exposures, on the order of 4 to 4.5 minutes. Those images were bright but blunt. The nucleus was overwhelmed by a large glowing coma that washed out fine structure. They showed motion in rotation, but little else. Then came January 22, 2026. On that date, Hubble again observed 3I Atlas, this time using exposure times of roughly 170 seconds, comparable to what many amateur astrophotographers use from the ground. These images struck a balance between sensitivity and resolution. They were bright enough to capture faint features, but not so bright that everything collapsed into a featureless blob. At the time, these data had not yet been fully processed or highlighted in official releases, but they were available for anyone willing to download and analyze them. When those January images were examined carefully, they immediately stood out. Even in relatively raw form, without aggressive filtering, multiple narrow features could be seen extending away from the nucleus. At first glance, they resembled jets, the collimated streams of gas and dust commonly seen when sunlight heats localized regions on a comet's surface. But instead of one or two dominant jets or a fan-shaped spray, there appeared to be several, emerging at different angles. Some of the earliest public discussion of these features came from researchers associated with the work of Avi Loeb, who shared processed versions of the Hubble images on Medium. Using a Larson-Sekanina rotational gradient filter, a technique designed to emphasize asymmetries in rotating cometary comae, they highlighted three narrow jets spaced at roughly 120-degree intervals around the nucleus. The symmetry was striking. Three evenly spaced jets suggested an underlying regularity, and the image quickly circulated online as evidence that 3I Atlas might be unusually well organized. Yet image processing is not neutral. Filters enhance some structures while suppressing others, and they can sometimes create the impression of simplicity where none exists. When the same January 22 Hubble images were inspected with minimal processing, a more complicated picture emerged. One of the supposed three jets, particularly the one extending downward in many filtered images, appeared to split into two distinct components. Fainter features became visible when brightness and contrast were adjusted carefully. Rather than three clean outflows, there seemed to be a cluster of jets, overlapping and diverging at slightly different angles. As more frames were aligned and compared, the complexity grew. Time-lapse sequences constructed from the 6 usable Hubble exposures showed the object wobbling subtly, though it was not immediately clear whether this motion was intrinsic to the comet, an artifact of Hubble's tracking, or a consequence of exposure differences. After aligning the images on the comet itself, the wobble largely disappeared, but the structural complexity remained. Jets brightened and faded, some pointing sunward, others angled away, their relative intensities changing from frame to frame. Beyond the jets, something else became apparent: tails. In earlier Hubble observations, no obvious tails had been visible. The long exposures of late 2025 showed only a diffuse coma. In the January 22 data, however, elongated structures could be traced extending far from the nucleus. At least 2 major tails appeared on opposite sides, and with careful processing, additional tail-like features could be discerned. In total, it was possible to argue that 4 distinct tail structures were present, a configuration rarely seen in ordinary comets. Colorized versions of the images added another layer of information. By mapping intensity variations to color, subtle dips in brightness became easier to spot. V-shaped regions of lower intensity suggested shadows or regions where material was absent, implying that jets were carving out channels in the surrounding coma. These features reinforced the impression that the outflow pattern was not simply 3 evenly spaced streams, but a more intricate, almost snowflake-like arrangement radiating from the nucleus. This observational complexity matters because it sets the stage for a broader debate. 3I Atlas is already unusual by definition. It is the 3rd known interstellar object detected passing through our solar system. Unlike long-period comets, which originate in the distant Oort cloud, interstellar objects arrive from entirely different stellar environments, carrying with them the physical histories of other planetary systems. Even so, astronomers expect some commonality. Physics is universal, and comets, wherever they form, are still governed by the same thermodynamics, chemistry, and mechanics. What makes 3I Atlas provocative is that its peculiarities extend beyond morphology. Avi Loeb compiled a list of features that he considers anomalous when taken together. He does not present these as proof of anything artificial, but as statistical tensions that, in his view, deserve careful scrutiny. One of the first points Loeb emphasizes is orbital geometry. 3I Atlas follows a retrograde orbit, meaning it moves around the Sun in the opposite direction to the planets. Retrograde motion itself is not unheard of, but what stands out is how closely its orbital plane aligns with the plane of the solar system. For an interstellar object arriving from a random direction in space, such alignment is considered unlikely. Loeb quantifies this as a small probability coincidence, one that becomes more interesting when combined with others. Timing is another element. 3I Atlas passed perihelion, its closest approach to the Sun, in a way that limited observations at precisely the moment when activity might have peaked. From Earth, the object was near the Sun in the sky, making it difficult to observe. Loeb frames this as another fine-tuning. The object was bright enough to matter, yet conveniently placed where its most active phase was partially hidden from view. Planetary encounters also feature in the anomaly list. Calculations show that 3I Atlas passed relatively close to Mars and Jupiter, with distances that appear, in Loeb's words, curiously well-tuned. Close approaches to massive planets can significantly alter an object's trajectory, but the geometry of these encounters adds another layer of apparent coincidence. Jet behavior returns as a recurring theme. Sunward jets are not unheard of in comets, but they are usually transient, tied closely to localized heating. In 3I Atlas, a prominent sunward jet appears both before and after perihelion, suggesting a persistent orientation. Loeb notes that maintaining such directionality would be challenging for a naturally tumbling, irregular body unless its rotation axis were aligned in a particular way. Indeed, rotation is another point of interest. Early observations suggested that the rotation axis of 3I Atlas was aligned within a few degrees of the Sun object line as it entered the solar system. For a randomly oriented interstellar body, this alignment again appears statistically unlikely. If correct, it would help explain the persistence of sunward jets, but it raises questions about how such alignment arose in the first place. Some of the jets appear to be active even when they should be on the night side of the nucleus, shielded from direct sunlight. In ordinary comets, night side activity can occur if heat is conducted through the surface or if volatile materials are exposed, but sustained, well-collimated night side jets are not common. Loeb highlights this as another deviation from textbook comet behavior. The January 22 geometry itself adds to the list. On that date, the Earth-Sun 3I Atlas alignment was within less than a degree, producing an unusually sharp opposition effect. The resulting antitail, a structure formed by large dust particles reflecting sunlight back toward the observer, lined up almost perfectly with the Sun-Earth axis. While opposition effects are known, such precise alignment again feeds into Loeb's broader pattern of coincidences. Beyond geometry and dynamics, composition introduces further questions. Spectroscopic observations of 3I Atlas indicated an unusual ratio of nickel to iron in its gas plume. Nickel is present in comets, but typically in proportions comparable to iron. An excess of nickel, especially in gaseous form, is not easily explained by standard models of cometary composition and sublimation. Dust properties add another layer. The antitail observed in 3I Atlas implies the presence of relatively large dust grains, heavy enough to resist being blown away by the solar wind. Such grains can exist, but their prominence suggests an atypical size distribution in the material being released. There are also reports, drawn from infrared observations, that icy fragments present before perihelion seemed to disappear afterward, while the abundance of organic gases increased. This shift in composition across perihelion is not impossible, but it complicates simple narratives of gradual heating and sublimation. Optical behavior rounds out the anomaly list. 3I Atlas exhibited extreme negative polarization, meaning that the light it reflected had unusual polarization properties compared to most comets. Polarization depends on particle size, composition, and surface structure, and such extreme values suggest that the dust environment around 3I Atlas is unusual. The object also brightened rapidly near perihelion and appeared bluer than the Sun, another combination that stands out in comparative studies. Individually, each of these features might be dismissed as an outlier or explained by invoking uncommon but natural conditions. Interstellar objects, after all, sample a vast diversity of environments. But Loeb's argument is cumulative. When many low-probability features appear together, he suggests, the burden on conventional explanations increases. This is where the earlier observational work becomes crucial. The detailed jet and tail structures revealed by the January 22 Hubble images underscore how sensitive interpretation is to data quality and processing choices. A simple narrative of three symmetric jets dissolves into a complex, evolving pattern when examined closely. That complexity does not automatically imply anything exotic, but it does caution against oversimplification. Science advances by confronting such tensions head-on. For 3I Atlas, the data are real, the measurements are public, and the anomalies are defined quantitatively, not rhetorically. Whether future analysis will reconcile them within existing models or require new thinking remains an open question. What is clear is that 3I Atlas has already fulfilled one of the most important roles an interstellar visitor can play. It has forced astronomers to look more carefully, to question assumptions about what normal looks like when the sample size is small, and to recognize how much information can be hidden in plain sight until geometry, timing, and curiosity align. In that sense, the object is less a mystery to be solved than a reminder of how much there still is to learn when something truly foreign passes through our cosmic neighborhood.